Today we'll discuss about work, energy and power, the second chapter of class 10. What is work we have already learned earlier. I just make you remember once. What is work? What is the definition of work? Now work is said to be done when a force is applied on a body and the body is displaced along the direction of the force. Assume this is a body. Okay, you are applying a force on it. If initially the body is here at point A, and now due to the application of force the body is displaced from A to point B. Okay, so if we measure here the displacement is S, so we can say that the work is done when a force is applied and the body is displaced. Now that second question has come, how do we measure it? That is measurement. So to measure the work done, we have to take a product of force and displacement along the direction of the force. Force and displacement along the direction of the force. Here you have to remember one thing, that we have just point one sentence, that is along the direction of force. That means if we apply the force on a body and it displaces along the same direction, then only we can able to write down work done W equals to force into displacement. Up to this we have learned earlier, I think in class 7 or 8, and now we will go in little detail. What is it? See, in this diagram, in which direction we are applying force, the body is displaced along same direction. Now I have given you an example. What is that example? Assume we have seen several times the little children are playing with the toy car. Okay, they are not having any remote control or such thing like that. It is made by plastic. They are having some wheels and they have tied the thread in front of the car, and using the thread they pull the car and the car moves in front. Okay, so why I have shown you this diagram? What is the reason behind it? The only reason is that here you see in which direction we are applying force to pull the car is displaced in another direction. Okay, see, there is an angular displacement between them. The force is applied along the tension we are applying by thread and it displaces in a straight line. That means there is an angular displacement. So if there is an angular displacement, so we cannot able to use this equation where W equals to force into displacement, because we have mentioned here that work is done, or we can able to calculate the work done when the force is applied in which direction the body displaces also in same direction. But what will happen if the body is not displaced along same direction? For this case we have to take it. Okay, for this case how we have to find out the work done? And for this case we are having two ways to measure the work done. Let's see. So first one, we have to find out the work done by finding the component of displacement along force. The component of displacement along force. What we are trying to tell? See, the diagram, we are just taking it from here. We just cut it and paste it here. So this is the direction of force. This is the direction of displacement. So the point of intersection, that is O. This point we are taking, it is A, and this point it is taking, it is B. So along OA we are applying force, and along OB the body is displaced. So first we have to find out the component of displacement along force. Means along force, along OA, how much OB is acting or how much displacement is occurred. Okay, it is little tougher for you, but try to understand, you will get it. Force and displacement both have different direction. we want to express the displacement along the direction of force. Okay, along the direction of force, how much displacement occurs. So how we can able to find it out? For this case, we have to draw a perpendicular from B to OA. Okay, so this is a perpendicular from B to OA. Assume this point is C. Okay, so what is OC? Now OC tells us component of displacement along force. Okay, along force component of displacement. See here, I just want to show it very easily. In your book the thing is been explained here, it is little critical, but if you read this portion also you will understand. If you understand this thing what we just want to express. So here you see the force is acting along this direction, and now along this direction we have taken the displacement also. So we can find out work done is equals to force into displacement along the direction of the force, that is OC. And now problem is that what is the OC? What is the value of OC? We don't know. We know the total displacement is S, which is denoted by OB, and here is the angle between them, that is theta. Then how do we find it out? In this case we are taking a triangle OBC. You see it's a right angle triangle because this we have drawn a perpendicular. Okay, so as it is a perpendicular, so we can say it is the hypotenuse OB, and OC is the base. So we can say that from OBC, OC by OB, base by hypotenuse, that is equals to what? Cos theta. And OC equals to OB cos theta, and OC equals to, if I put the value of OB equals to S, so that is S cos theta, right? And now put the value of OC here, so W equals to F S cos theta. That means if there is an angle between force and displacement, then the work done will be force into displacement into cosine of the angle between them. How we are finding it out? We are finding it out by measuring the component of displacement along force. Now the second part we are going to do, that is by finding the component of force along displacement. Exactly opposite thing. In the previous part we have done component of displacement along force. Here we are doing the component of force along displacement. Now see, this component term is little new to you. Okay, but I think you can able to understand whenever we will go to class 11, then it will be very much familiar to you. So the same diagram we have drawn here. So this is force, this is displacement, this is the O, this is A, this is B, and this angle is theta. So along OA we have shown force, along OB we have shown displacement. Now we just want to find the component of force along displacement. So in case when we finding out the component of displacement along force, for that case we have drawn a perpendicular from displacement axis, this is known as displacement axis, to force axis. And now here we have to find out the component of force. For that case we have to draw a perpendicular from force axis to displacement axis. So from A point we have drawn a perpendicular here. So assume it is C. Okay, so what is OC here? OC, this line segment represent the component of force along displacement. Okay, so now we have to go on by our previous idea, that is work done equals to force into displacement. So what force we have to take? We have to take the component of force, that is OC into S. The total displacement is S, it is there. Okay, because you see the direction of both the force and displacement, it is same. It is our only target. We have to take the component in such a way so that the direction of force and displacement, both the things will be same, and then only we can use it by this formula. And now see OC, what is the value of OC? We don't know. We know the value of OA is F. So for that case also we have to take a right angle triangle. What is the right angle triangle? We have to assume here triangle OAC. Okay, from OAC we can write down OC by OA, that is equals to cos theta. OC by OA equals to cos theta. So OC equals to OA cos theta, or OC equals to OA, means OA equals to this line segment represents F, so it is F cos theta. Okay, put the value here, so it is F cos theta into S. That means W equals to Fs cos theta. See, the previous equation what we have discussed earlier, the same thing we got, that is W equals to Fs cos theta. Now we'll discuss the spatial cases. Okay, this one is very important. Please see it properly. What is the spatial cases? If I am taking the first case, the first case tells us the direction of force and displacement is same. That means in which direction force is applied, the displacement is also occur in same direction. It is the F, and here it is the displacement S. So in this case, what will be the angle between force and displacement? If I am talking about angle, see, the direction is same, so angle will be 0. If angle is 0, if we put it our equation Fs cos theta, so we have to write down Fs cos 0. So Fs cos 0, what is the value of cos 0? That is 1. So it is F into S. See, we have got the previous equation we have learned earlier, that if the force and the displacement occurs in same direction, then work done is equals to force into displacement, and it is called the maximum work done. It is known as the maximum work done case. That means if you are applying force and the body displaces along same direction, in that case only you will get the maximum work done. Okay, so when theta is 0, that means there is no angle. Okay, now we have to come the point number 2. Point number 2 is if the direction of force and displacement is opposite to each other. Okay, how we have to explain it? See, it is a very easy thing. If you want to understand, then it will be very much clear to you. Assume I have kept one magnet here. Okay, magnet, you know, bar magnet, it's north, it's south. Okay, you have taken another magnet, it is north. Okay, it is south and it is north. So if this magnet is approaching this one, okay, then what will happen? They will repel it. Okay, so as they will repel, you see the force of repulsion is acting in this direction, but you are applying force in this direction. You want to approach the another south pole nearer to this south pole. Okay, so the displacement is occur in this direction. Okay, now if I want to find out the angle here, if I want to find out the angle, that is the angle between F and S, theta, that is equals to how much? That is 180 degree, because you see in this direction the force is applied, in this direction the displacement is occur, force, displacement, So this angle, that will be 180 degree. Okay, so if it is 180 degrees, then what will be the work done? F is cos 180 degree. So what is the value of cos 180 degree? It is -1. So it is minus Fs, and this is known as negative work done. Okay, so if it is asked you that what is the condition of negative work done, the condition of negative work done is that when the force is applied in one direction, the displacement occurs exactly in opposite direction, then only we'll get the negative work done. Now we'll go to the third and very interesting thing. What is it? See, the third case it is left. It is told that if the angle between force and displacement is 90 degree. The angle between force, that means if the force is applied in this direction, the displacement is occur here. If the angle is 90 degree, here theta equals to 90 degree, then the question may be asked, then what will be the work done? Because work done equals to F is cos 90 degree, and cos 90 degree means 0. So W equals to 0. That means here work done is 0. The work done is 0 here. You are applying force, the body also displaces, but your work done is 0. Example, very easy examples are there. Okay, assume if a coolie if a coolie taking some load on his hand and moves in front. In this case, what will be the work done? So when he has taken a load here on his head, so the force of attraction towards the gravity, it is acting downward. There the force is acting, and the man is displaces along this direction. So direction of force and direction of displacement, this is the force, this is the displacement. The angle between them is 90 degree, and then work done will be 0. You will see the man has done some work, but eventually the work done is 0. Similarly, if the same thing occurs by a person, if he is going by taking a suitcase on his hand, or if it is occurred by you also, if you have taken bag at your back and move forward, in this case also the work done should be 0, because the force of gravity is acting downward and the displacement is occur here or here, whatever in the direction may be, the angle is 90 degree. And if the direction of force and displacement is perpendicular to each other, then your work done should be 0. Second example here we have to discuss is a very common one. See, in the previous part only we have discussed uniform circular motion. Assume if a body moves in a uniform circular motion. Okay, so the direction of displacement at any point, okay, at any point the direction of displacement in uniform circular motion is along its tangent. Okay, the direction of displacement, in which direction the direction of displacement occur, the direction of velocity is also in same direction. And if I am telling the force is acting on the body, we know for uniform circular motion the centripetal force is acting, which is acting towards the center, and we know it is acting radially inward, means if it is the radius, it acts along the radius towards the center. Now we know the angle between radius and the tangent, it is 90 degree. And as it is 90 degree, so if a body moves in a uniform circular motion, in this case its work done will be 0. Okay, no work is done, because the angle between direction of displacement and the force, it is 90 degree of each other. That means the work done is 0. That means we can say, if the earth is moving around the sun in circular path, okay, so if it moves in a circular path, then the force of attraction, it is acting towards the sun, because as it is in center, the direction of displacement is acting here, so the angle is 90 degree. So as the angle is 90 degree, so here also the work done by earth, it is 0. No work is done by earth. Okay, I think it is clear enough. Okay, so if a body possesses a motion in uniformly circular path, then also the work done should be 0. Okay, now we have got two conditions where we can say the work done will be 0. Number one, if no displacement occurs, and number two, if the angle between force and displacement is 90 degree. Okay, and this condition is known as, this is the minimum work done condition. Okay, this condition is known as minimum work done. So if the question has come, in which condition maximum work done occurs, so when angle is 0 degree, in which condition minimum work done has occurred, when angle is 90 degree. That things we have to remember. Now we'll discuss little bit about work done by the force of gravity. It is also one example we want to show it, and it is important later whenever we have to discuss the energy portion. So please see it properly. Work done by the force of gravity. What is it? Let's see. Assume we have taken a height here. The height is h. An object is kept at ground. Okay, this is the object. It is kept at ground. Assume the mass of the object is m. So if it is the mass of the object, the weight which is acting downward, that is w. I have written weight here because if I have written w, then you might be compared with the work done, because work done also denoted by w. So weight is equals to m into g, where g is the gravitational acceleration that we have known. If I want to take the object and want to keep the object at a height this h, so we need to apply a minimum force to lift it. That should be mg, that is the weight of the body. If I want to lift a body, if I want to take a body, so in this case also you have to apply a force that will be equal to its weight, otherwise you cannot able to lift it. So how much force you have to apply? Now force F equals to m into g. In which direction the force will be applied? The direction of the force will be upward, because I want to take it. Direction of the displacement, you see, the direction of the displacement is also here in this direction, that is h. You are displacing the body by a height h also, that is also in upward direction. So the direction of force and displacement is same. So we can say the angle between force and displacement is 0. So W equals to F S cos 0. That means F into S. So what is F here? Here F is mg. What is S here? How much the body displaces from ground to the height? That is h. Okay, so we can say our W is equals to mgh. This is the work done by the force of gravity. And now the next thing will come, that is the unit of work done. See, you have learned earlier also what is the unit of it. So if we have taken the first equation, W equals to Fs, so the unit will come, the unit of force into unit of displacement. So unit of force into unit of displacement. So if I want to find out the SI unit, so SI unit of work done is Newton into meter. So Newton into meter, that we have represent by another unit, that is joule. Okay, so joule, which is denoted by capital J, this is the SI unit of work done. And if I want to define 1 joule of work done, so it is clear 1 joule equals to 1 Newton into 1 meter. That means by application of 1 Newton force, if a body displaces by 1 meter, then the work done will be 1 joule. Okay, work done will be 1 joule. And now we will go for the CGS unit. The CGS unit, what? In CGS unit, the dyne force unit will be dyne, and displacement will be centimeter. So 1 dyne into okay, and that is known as arc. And 1 arc is equals to 1 dyne into 1 centimeter. That means by application of 1 dyne force, if the body is displaces by 1 centimeter, then the work done is known as 1 arc. If I want to find the relation between 1 joule and 1 arc, see, 1 joule is equals to 1 Newton into 1 meter. So if I convert 1 Newton to dyne, we know 1 Newton equals to 10 to the power 5 dyne, and 1 meter equals to 10 to the power 2 centimeter. So it is 10 to the power 7 dyne centimeter, and 10 to the power 7 dyne centimeter means 10 to the power 7 arc. Okay, so that is the relation between joule and arc. But see, the unit joule, it is a very smaller unit. So for that case, we generally use for work done, that is kilojoule. 1 kilojoule equals to 10 to the power 3 joule. Megajoule, mj, that is 10 to the power 6 joule. Okay, and gigajoule, that is 10 to the power 9 joule. So these are the larger unit of work done. Okay, now we'll go for the another topic. Okay, that is power. Comparatively, it is very easier if I'm talking about power. What is power? Very common thing. If I have given some work, same work, okay, of 2%, so one can able to do it very fast, and one will take much time than the previous person, than the first person. So those who can able to do the work very fast, we can say his or her power is more. See, we are very much familiar with the Avenger or something like that. If it is told to us to go Kolkata or London, whatever it may be, it will take some time. But if I am telling the same thing to Spider-Man, if we believe that this type of person is there, so he can able to reach in one point to another point very fast than us. That's why his power is more than us. Okay, he's more powerful than us. So basically, power is what? The power is rate of doing work. Rate of doing work, that is known as power. How? See, if I want to find it out power, the power P equals to W by T, work done per unit time. So if your time is less, then definitely your power will more. If your time is more, then your power will be less. Very easy thing. Next, we will go for the unit of power. So if I am talking about the unit of power, that will be unit of work done by unit of time. So just now we have seen the SI unit of work done is joule. Okay, and SI unit of time is second. So joule per second, that should be the unit of power, and that is known as watt. Okay, that is known as watt, which is denoted by capital W. Okay, and now if anybody tells us to define 1 watt, so when 1 joule of work is done in 1 second, then the power is known as 1 watt. Okay, and as I have told earlier that the unit of basically work done, it is very lesser, so the unit of power watt, that is also very less. So that's why we generally use kilowatt, megawatt and gigawatt. So kilowatt equals to 10 to the power 3 watt, megawatt is 10 to the power 6 watt, gigawatt is 10 to the power 9 watt. Apart from this also we have uses several general units like horsepower. Okay, so horsepower, it is also a unit of power. So 1 HP equals to 746 watt. Okay, these are the general unit of power. Okay, now we have to find a relation between power and force. Okay, power and force and velocity. So we can say relation between power, force and velocity. How we have to find it out? A very easy thing. See, this we have done to do some numericals. So power equals to W by T. We have no. W is what? W is equals to force into displacement if the displacement occurs in the same direction where we apply the force. That means basic thing is this thing will happen if the motion is occurred or force is applied, and for that what motion we have seen, that is in one dimension. We have read motion in one dimension in previous class. Okay, that means in which direction force is applied, the displacement occurs in same direction. So F into S by T, or F into S by T. So S is the displacement, T is the time. So displacement by time is the velocity, F into V. So we can say power equals to force into velocity. That is the relation between power, force and velocity. Okay, this is the relation. Okay, now we will discuss a difference between work and power. Okay, difference between work and power. Okay, simply this one, I think it is there in your book. So what you have to do, you have to read the book. I'm just telling the definitions first, telling the difference first. First of all, work done is basically work is done when a force is applied and the displacement occurs, and it is measured by force into displacement. And power, it is the rate of doing work. If you see, it doesn't depend on time. Power, it depends on time. The unit of work is joule, but unit of power is watt. Okay, these are the difference. My suggestion is you go through the book. I think you can able to understand. Next, the last part of the first topic. Okay, the topic we just want to discuss in the last part of the topic, first topic, that is energy. If anybody asks you what is the definition of energy, that we all know, the energy is basically the capacity of doing work or the ability of doing work. So we can say ability or capacity of doing work. Okay, see, work and energy, both the things are same. It is known as equilibrium. We can say work and energy is equilibrium. So how much, see this sign we have seen in chemistry now, whenever we have shown you any equilibrium reaction, here also we have shown the same type of thing. Work and energy are equilibrium to each other. Equilibrium means if you have done some work, it will justify that you are having such amount of energy. Or if some energy you have calculated, that means some amount of work is done the body, that's why it gain that amount of energy. So work and energy, it is basically same thing. Okay, both are scalar quantity. Work is a scalar quantity, energy is also a scalar quantity, power, it is also a scalar quantity. And now we'll coming to the SI unit. So what is the unit of energy? So it's like the same with the work done, that is joule. What is the CGS unit of energy? The CGS unit is also same as like we have done earlier, that is arc. But problem is that these units are very smaller. Okay, why we are telling it is a smaller unit? Just now we have learned 1 watt equals to 1 joule per 1 second. That means if 1 joule of work is done in 1 second, then we can say our power is 1 watt. Now from here we can say 1 joule is equals to 1 watt into 1 second. That means if 1 watt power of an instrument, I mean if it works for 1 second, then it is known as 1 joule also. In another word, that is joule equals to watt into second. Now I have given you a quick example of it. I will elaborate it in electricity chapter, but I think you can able to understand it. You have done earlier also. Assume whenever we have taken a bulb, okay, nowadays some LED bulbs are there. So assume a bulb is 20 watt. Okay, a bulb is 20 watt. So if I am telling a 20 watt bulb is there, so how much energy is consumed by it? So in 1 second we can say it is 20 watt into 1, that means 20 joule. So 20 joule of energy is consumed when 20 watt of bulb it is used for 1 second. So you see it is very smaller unit, because in this way if you find out that how much a bulb glows in your home, that will be some hour. So 1 hour equals to 3600 second. If it is work for 6 or 7 hours, so 3600 into 6 into 20. So the number, the amount of energy it is coming, it is very large in number for joule. For that case we have taken a commercial unit. So what is commercial unit here? A commercial unit is equals to known as kilowatt hour. And we know 1 kilowatt hour is equals to, that we have done earlier also, 1 kilowatt equals to 1000 watt, 1 hour equals to 3600 second. So it is 3.6 into 10 to the power 6. Okay, this much amount of joule. So this one we have taken the commercial unit and it is known as 1 unit. So in basically the electricity bill that comes to our house, that is come by this unit system. Okay, and next it is very common, it is calorie. It is also 1 unit of energy. Mainly it deals with the heat energy. Okay, so what is the definition of it? If a water, 1 gram of water, its temperature is increased from 14.5 degree to 15.5 degree centigrade, then what work has to be done, that is 1 calorie, and that much energy is consumed by it. Okay, and another unit of energy is electron volt. Okay, so electron volt means if 1 electron is kept in 1 volt, that is known as 1 electron volt. So if 1 electron is kept in 1 volt, what energy is possessed by it, that is called 1 electron volt. So 1 electron volt equals to 1 electron into 1 volt. 1 electron equals to 1.6 into 10 to the power minus 19 into 1 volt. So this much coulomb, to 1.6 into 10 to the power minus 19 coulomb into volt, that is 1.6 into 10 to the power minus 19 joule. So that is also 1 unit of energy. Now simple thing, the difference between energy and power. I think it is also given in your book. Energy is the capacity of doing work, power is the rate of doing work. Energy doesn't depend on time, power depends on time. The unit of energy is joule, unit of power is watt. So these simple things are there in first chapter, okay, first part. Okay,